we're making a bit of a shift now from charges to magnets and from electric field to magnetic field. We're going to circle back in a little bit, and you'll see that they're actually not as different as you might initially think. But let's start with some basic facts that we know about magnets and magnetic fields. So first off, with magnetism, you're probably familiar with an image of a magnet that looks something like this. We have some piece of iron, usually for magnets, and that piece of iron has a north pole and a south pole. Now, that looks a lot like what we did for electric charges. We called it a dipole when we had, say, a rod here that had plus side and a minus side. And if we were to, say, cut this thing in half, we'd end up with a positively charged piece and a negatively charged piece. Now, magnets are a little bit different in that if you cut a magnet in half, like this, you'd end up with, well, a magnet that has a north pole and a south pole, and another magnet that has a north pole and a south pole. As far as we can tell, well, maybe. As far as we can tell, there's no such thing as a magnetic monopole. We can't have just a north pole or just a south pole on a magnet. It's actually an area of research right now, and last summer there was an announcement that some researchers working in Antarctica, I think, had they think, detected magnetic monopoles. So, we'll probably be hearing more about that in the near future. But for now, we're going to work with the knowledge that magnets are always dipoles. They always come with a north and a south pole. Now, magnets can also produce fields. They do produce fields just like charges do. So with charges, we call them electric fields. With magnets, we call them magnetic fields. And you would have heard of that before. Now, if we put one of these magnets into a magnetic field, it's going to rotate to line up with that magnetic field. So the biggest magnet around is the Earth. So it's a really big magnet. Magnetism comes from rotating iron and other materials. The iron is what does it. Liquid iron inside the Earth spins around and generates this electric field, and also causes certain metals on the Earth to become magnified. I think it said electric field, but I meant magnetic field. And so the Earth behaves like a big magnet with its south pole up here and its north pole down here. And you might think, well, that's a little odd. Shouldn't we usually draw the north pole on top and the south pole on the bottom? Well, yeah, this is the north pole of the Earth, but it's a magnetic south pole, which is why when you have a compass, and you hold a compass out, the north pole of the compass points toward the south pole of the Earth, the south magnetic pole of the Earth, which is at the Earth's north pole. So this is the Arctic Circle up here, this is Antarctica down here. So up in the Arctic Circle we have what we call the North Pole that's actually a south magnetic pole. And so, these little magnets, if we have them somewhere over here, they will line up so that we have north and south here because of the way that the field on this on the Earth works out. So it has a shape just like we had with those dipoles with charges. So it's something kind of like this. And so the North Pole is going to point toward this. The North Pole on this magnet points toward the South Pole on this one, on the Earth magnet. Now, this magnetic field we represent as a B. B is the magnetic field. I guess just too many things already had M with them, so it's a magnetic field, it's a B. Sometimes we call them B fields as a result. Now, we can see that since this magnet is caused to rotate due to this magnetic field, there must be some force acting on this magnet. Well, it turns out that it's not just magnets that receive a force from magnetic fields. If we have a charge moving through this magnetic field, it has to be moving. But if it's is moving through this magnetic field, the charge actually gets a force as well. And this is where we're going to revive the right-hand rule, which is why you can see me and not just what I'm writing, because I need to be able to show you my right hand. So, if we want to figure out the the force on a moving charge moving through a magnetic field, the force is going to be equal to the magnitude of the charge. So it just always a positive number there. Don't use a negative, even if it's an electron. Just use a positive number. I guess that would just be for the magnitude of this force. We'll come back to that in just a minute. So here, you actually would use the positive or negative. Sorry, I messed up there. And then the equation here is V cross B. So it's the velocity vector crossed with the magnetic field vector, and then multiplied by this scalar quantity of the charge. If we want to know just the magnitude of that force, then we'll do just the magnitude of the charge times the magnitude of V times the magnitude of B times the sine of the angle between them. So most times what we'll do in these problems is calculate a magnitude with this equation. So the amount of charge times the speed times the amount of magnetic field times the sine of the angle between these two vectors. That's the amount. And then we'll just use the right-hand rule to figure out direction. So that's really what is being expressed by this equation. That gives us information about direction as well instead of just about magnitude. So Q times V cross B is the equation. So let's say we have a magnetic field that is pointing into the board. Remember this notation? We have the little X's, that's like the tail end of an arrow. That's the way to think of it. And if we had little dots, that'd be like the tip of the arrow. So this field is pointing into the board. And we'll say that our magnetic field here is about 0.001. And the units for magnetic field that we use most commonly are teslas. 0.001 teslas. And let's say we take a positively charged object and maybe have a Q of, say, 0.1 coulombs, so big charge there, and we'll have that moving in this direction. And how about a speed of 100 meters per second? So first off, the magnitude for the force that's going to be acting on it. So the magnitude of the force would be equal to, let's see, the magnitude of the charge is 0.1 coulombs times, I think I'm getting off the screen here, I'll go here. So the magnitude of the force is going to be 0.1 coulombs times the speed, 100 meters per second, times the B field, the magnetic field, 0.001 Tesla, times the sine of the angle. Well, our vector for velocity is this direction. For magnetic field is into the board. That's a 90-degree angle. So times sine of 90 degrees. So the magnitude of our force then is going to be, let's see, 0.1 times 100 is 10. And then divided by 1,000, so that'd be 0.01 newtons. And then sine of 90 degrees is just 1, so 0.01 newtons is our magnitude. We also need the direction with this. So to do the cross product, remember the right-hand rule here, it's V cross B times Q. So to do V cross B, to get the direction on that, you're going to take your pointer finger and point it in the direction of V, the first vector there. So pointer finger in this direction. The middle finger then is going to point in the direction of the B field. So here's my pointer finger. My magnetic field, it points into the board. So if I extend my finger like this, that's the wrong way. I had to rotate my hand in this direction. So now my middle finger is pointing into the board. my pointer finger is pointing in the direction of the velocity. And my thumb, when I extend that, that's going to point in the direction of the force. So my force is acting downward. And so we can see from this that we're not going to travel in a straight line. The charge won't travel in a straight line here. It's going to travel in kind of a curved path. So this force with the direction would be 0.01 newtons down on the whiteboard here. Not into the page, but vertically downward. Now, we'll get back to what path these things follow in the next few videos.